Hello everyone, this is Dr. Dhiman and I welcome you all to this physics tutorial series in class 11 physics. So I am solving the NCERT textbook problems here in this playlist. So in this video we will solve the problem number 2.2 from the chapter number 2. In this problem we have to make some estimate. This problem is a bit long, therefore I have already written the answer in this video and I will explain you step by step how we have obtained this results or how we have estimated these measurements. Okay, so in this question we have to consider some upper bounds. Whenever we have a complex number, we have to consider the upper bound of the quantity. So we have here 5 parts. These are the 5 parts. So we have to make some estimation point wise, okay, part by part. So let us consider the first problem. I am not reading out this question. Why? Because this problem is going to be a little bit lengthy and I hope you will understand. If you have any question, please put it in the comment section below. I will try to answer it. So let us consider the first problem. In the first problem, we have to estimate the total mass of the rain clouds over India during the monsoon season. So we know that area of India is equal to 32,87,259 this much of square kilometer. This much of square kilometer we have. So this much we can approximate. So we can approximate to the upper bound as it is given in the question. So let us consider 3.3 into 10 to the power 6. From this value we have approximated it to be 3.3 into 10 to the power 6 this much of square kilometer, or we can write it as the kilometer square also. Next we have to consider this kilometer square and we have to convert it to its meter unit. So 1 kilometer means it is 10 to the power 3 or 10 cube meter. So kilometer value can be replaced with this kilometer unit can be replaced with 10 to the power 3 meter, and we have a whole square here. So here we'll have a area of the India will be 3.3 into 10 to the power 12 this much of meter square. Now let us assume that the average rainfall height is this much of centimeter. This is the average rainfall height as per the meteorological department of India. So 10 centimeter is equal to 0.1 this much of meter. Now volume of the rainwater, volume means this area, surface area by into height. So it will be the volume. So here we have A into H. A value we have obtained this one, okay, and this small h value we have this one. So we have to multiply these two, and here we'll have 3.3 into 10 to the power 11 this much of meter cube. So this is the volume of the rainwater. Now the density of the water. So the standard density of water is 997 this much of kilogram per meter cube. That means in 1 meter cube of volume we have this much of kg, this much of mass of water. That is the density. This density is denoted with rho. So we can approximate this 997 kg per meter cube as 10 cube kg per meter cube. Now I hope you understand this. Now we know that the density is the mass divided by volume. Okay, so therefore mass is equal to volume into density. Okay, this much I hope you are clear. Now mass of the rainwater, so we can multiply volume with density. So capital V into rho, density is rho. So here this value is nothing but the V value, that is the volume, and this 10 cube is, this is the 10 cube. Here we have, this is the 10 cube, this is the density of the rainwater. Okay, so therefore the mass will be in the kg unit, and here we have got the mass is 3.3 into 10 to the power 14 this much of kg. Okay, so this is the total mass of the rain bearing cloud over India during the monsoon. Okay, so this is the first part solution. Now let us come to our second part. So in the second part we have, this is the problem, the mass of an elephant. So here you have to understand one point. So what is the point? In this problem, second part, we cannot directly calculate, or it is difficult to calculate the mass of an elephant. So here I have written here, you can read from here. We cannot directly measure the mass of the body of an elephant, or we can say that, or it would be a time consuming process because of the non-uniform shape of the body of the elephant. We can use Archimedes principle to easily calculate the mass. So what is the Archimedes principle? According to the Archimedes principle, we have the upward buoyant force that is exerted on the body immersed in a fluid, whether it is fully submerged or partially submerged. This is equal to the weight of the fluid that the body displaces. Let us consider one boat. This is the boat. Okay, this is the boat structure. So in this boat, so suppose the base area is capital A, we have assumed. Okay, now when we immerse in water, the submerged water is suppose D1. So what is the D1? Let me show you here. This is the D1. So from here to here, this is the height is the D1 here. I hope you understand this much. Okay, now the base area is already we have assumed, because it is the same boat, it is capital A, base area is capital A. The volume of the displaced water by the boat only without the elephant, so this one is V1 is equal to A into D1. So this one is the D1 is the height, and this A is the base area. So here we have got that the volume of the displaced water by only the boat without the elephant is V1 is equal to A into D1. Okay, now we have put the elephant here. This is the elephant. I hope you will not make a fun of this elephant. Okay, so this is the elephant, and here we have the boat. Now this distance or this height, this will increase, and suppose we have a new value of D2. This is the new value, that is the D2. D2 is the height now with the elephant. With the elephant, the boat and the elephant, that is the boat and the elephant, this combination displaces the water somewhat higher, and it has a height now that is equal to D2. Therefore, the volume of the displaced water by the boat and the elephant combination is equal to V2, and this is equal to A into D2. Okay, now volume of the displaced water by the elephant only. So what will have the total volume we have to consider here, and we have to subtract only the boat volume. This V1 is the only both volume of displaced water. Okay, so here we can replace with AD2 and V1 is AD1. Okay, so we can take A common and we have D2 minus D1. Now let us consider the density of the water is rho. This is the density of the water. Now the mass of the elephant, what will be the mass? Mass is equal to volume into density, because the density is equal to mass by volume or mass per unit volume. Therefore we can say that the mass of the elephant is equal to volume into density. This mass is the volume and this rho is the density. Therefore the elephant has a mass of this much value. We have approximated the mass of the elephant. In the third problem, the wind speed during a storm. Suppose we have a storm going on and we have to measure the wind speed. So we will consider a balloon. Why we will consider a balloon? Because it has a very lightweight, and if we release or if we leave it floating in the air, it will move in the direction of the wind along with the speed of the wind. So suppose we have a balloon here at position A. This is the balloon and it is the position A at time 0, and after 1 second, suppose this balloon travels this much of distance from A to this B point, and now the balloon is here after 1 second. Why we are considering 1 second? Because we have to find out the speed. Speed is displacement per unit time. This is the speed definition. Okay, so at the beginning the balloon is at A, after 1 second it is at B. So here we can see this angle is theta. Therefore we can write theta is equal to d by h. This means this theta is proportional to small d and this is inversely proportional to the small h. Why? Because if we now suppose increase the value of d, so what will happen? This theta will be this much and this theta value will increase. It is directly proportional. If we decrease the d value, then this theta will decrease. This is directly proportional. This theta value is directly proportional to the value of the displacement. Now we can write this displacement. This displacement d is equal to theta into h. So this is the displacement. Since the balloon has very light weight, it will move with the speed of the wind. Okay, we can estimate the speed of the wind. This is suppose capital S, and this S is equal to the displacement, which will be equal to the displacement per, because this d is per second. This is the displacement in 1 second. Therefore we can write h theta, this much of meter per second, it will have the speed. Therefore, the wind has a speed of this much. Now, let us go to our fourth part of the problem. In the fourth part of the problem, we have the number of strands of the hair on your head. That means we have to count the number of strands of hair in our head. Let us assume that there is a uniform distribution of hair in the head. Why we have considered uniform distribution? Otherwise, it will be difficult for us to count the number of hair. We have made some approximation. We have to estimate the number of hairs in our head. Therefore, the number of strands of hair, this will be the area of the head divided by the cross section of the hair. That means one hair's cross section, this much of that means surface area it will cover in the head. Therefore, if we divide the area of the head divided by cross section of the hair, then we will obtain the number of strands of the hair. Okay, now let us consider the thickness or the diameter of the human hair. This thickness means this is the diameter. This to be 5 into 10 to the power minus 5, this much of meter, and in centimeter it will be 5 into 10 to the minus 3 centimeter. This is the hair you can see here, and this is the suppose cross sectional, because the hair has a circular cross section. Suppose we have a diameter of small d from here to here. Okay, this is small d. Therefore, the area of cross section of the hair, this will be pi r square. This is the formula, and r is equal to d by 2. R we can replace with d by 2. We have d value is 5 into 10 to the minus 3, so we'll put here. Okay, so here we will obtain this is the area of cross section of the human hair. Okay, now suppose the human head radius. Now we are considering the human head. We are considering it to be a spherical in shape, and we have assumed that we have a diameter of this head is equal to, this is equal to r, and this value is suppose 8 centimeter. We have assumed here. Therefore, the area of the head, what will be the area? It is the surface area. So here we'll have pi r square. Okay, pi means 3.14 into r means 8, therefore 8 square, this much of centimeter square, because this 8 is in centimeter. Okay, therefore this much of area in the head. Therefore, the number of strands, we have already seen that this is the area of the head divided by the cross sectional area of the hair. Therefore, we will have 10 to the power 7 this many number of human hairs in our head, considering that the distribution of the human hair is uniform, and we have assumed a spherical shape of the head, and we have estimated the number of hairs in our head. Now let us go to our fifth part of this problem, the final or the last part of this problem. In this fifth part of the problem, we have to estimate the number of air molecules in our classroom, in your classroom or in our classroom. Okay, suppose we can assume that the classroom has some length, it has some breadth, and it has some height. Let us assume that the length of the classroom is small l, breadth is small b, height is small h. Okay, therefore the volume of the classroom, this will be equal to the volume of the air that is contained in this classroom. Okay, now at NTP means normal temperature and pressure, 1 mole of air occupies 22.4 liter, this much volume in the atmospheric pressure, that is the normal temperature and pressure. Okay, this is the value at, this is the volume, that is the 1 mole occupies this much liter, means this is the volume. This liter we have converted into meter cube, this much is the liter. 1 liter is equal to 10 to the minus 3 meter cube. Okay, now we know that the number of molecules in 1 mole, this is equal to the Avogadro's number, and the Avogadro's number has a value of 6.023 into 10 to the power 23. Therefore, the air molecules density, this is again suppose we have rho, this is denoted with the density is denoted with rho. Therefore, the number of molecules per unit volume, this is the density. Therefore, 6.023 into 10 to the power 23 divided by 22.4 into 10 to the power minus 3, this much per meter cube. Okay, this many number of molecules per meter cube of volume. Therefore, we can write the number of molecules in the classroom. This will be density multiplied by volume. This is the density we have obtained from here. This is the density, and this density is multiplied with this the volume, L into B into H. This is the volume of the classroom. Therefore, this is the approximation of the number of molecules in the classroom. Thank you for watching. If you have any question, please put it in the comment section below. Also like, share and subscribe to my channel.